everyone. Welcome. Thanks for joining to this exciting webinar that we have. We are very excited and pleased to have ID Quantique, a pioneer in quantum communication, cryptography, and security, hosting this webinar. And they're going to talk about single photon detection and the future of quantum networks and computing. Our speakers today are Felix Gutierrez from the VP of Research and Tech, Giovanni Resta, R&D Scientist, and Tyle Stelzik, the Product Manager at ID Quantique. Just before I hand off a few housekeeping notes, please use the Q&A box down there on the Zoom to post your questions. There will be the Q&A at the end of the meeting in the last 10 minutes or so. And I will read your questions through the Q&A box and you can use the chat box to just communicate and introduce yourself and say who you are and where you are from. But make sure if you have any questions, post them on the Q&A and I would get to them at the end of the meeting. Just with that quick note, I would hand off the room to Felix. Felix, please go ahead. The floor is all yours.
Super. You see my screen?
Yes.
Perfect. Great. It's a real pleasure for me, Giovanni and Tal, to be here today. Thank you very much for being there. On your side, we want to tell you about single photon detection and the future of quantum networks and computing. So without further ado, let's just jump into the topic. And I'm going to start with the first line of the title, single photon detection. So what makes a good single photon detector? There's a couple of metrics that you want to look at. Maybe some will have to be at a higher level depending on your application. But let's do a review of this. The first thing, pretty obviously, is the system detection efficiency. What is the probability that your detector is going to tell you that there was a photon when there was actually one? Typically, everybody wants this to be as close as possible to 100%. Dark count rate, it's the opposite. When there is no photon, you don't want the device to tell you there's one. So everyone wants this to be equal to 0. Then you have the recovery time. So whenever there's a detection, a single photon detector will be off for a certain amount of time. And the smaller this time is, the faster you can detect light. So typically everybody would like to be this equal to 0. And then good timing precision, how precisely the detector is going to tell you that the photon arrived at a given time. And there's lots of protocols, quantum key distribution, for instance, where you need that kind of very small time precision. And something else that we're going to talk about today, which is photon number resolution, the ability for the detector to tell you that, hey, there was 2 photons at the input, and there you go, I'm telling you that it was, and you don't want this to be incorrect prediction that there was actually 2 photons at the end. We're going to talk about a lot about SNSPDs, okay? Superconducting nanowire single photon detectors. SNSPDs is the acronym. This is something that we develop, produce, ship and sell and ship. They offer today the best detection performance and possibilities. It's the best combination of high detection efficiency for many wavelengths. It can be very close to 100%. Very good time precision, tens of picoseconds or less than that in some situations, or very low dark count rate. For some detectors, we get below 1 count per second of dark counts. There are other metrics into which you may have to have a lot of performance in. One of them is extremely high detection rates, so say more than 1 gigacount per second, and excellent PNR performances. We're going to talk about this in this presentation. But before getting there, I want to talk about quantum networks and photonic quantum computing in 2024, and more specifically, the detection challenges that come along with these technologies. So let's start. The first kind of quantum network that you can think of is a QKD network. So QKD is for quantum key distribution, 2 boxes exchanging light at the single photon level, and that is able to generate a cryptographic key. So you can think of a network composed of several positions where there can be one or more than one QKD box, And then all the links here are going in this network are going to be used to generate keys between neighboring pairs. Once you have this, you can pop the key. I'm not going to go into the details, but you can do that. And that can allow any arbitrary pair in the network to do quantum key distribution. So that's something that we do at IDQ. We've been doing it for 20 years now. We have these different products. That Lattice XG is one of them. This is something that can be taken to a scale. This is an example here of a quantum key distribution network that was built in South Korea. It spans over more than 800 kilometers of optical fiber with many quantum key distribution boxes made by IDQ. It allows 48 government organizations to get keys for secure applications. So we're talking about politics, we're talking about medical, security, etc. So it's a very real world implementation of QKD today, and that's a network that is in production as of today. So that really exists in 2024. You can imagine that in some of these networks, there will be links that will have to generate a lot of keys because there's a lot of traffic in it. So in terms of the detection challenge, you need to be able to operate at high speed. And in some sections, you might have a lot of loss, and there's no repeater, classical repeater in quantum communication. So you need to have a very good single photon detector, very low noise and high efficiency. There's also QKD with satellites. And here I'm going to talk about the Eagle-1 project, which is the first space-based quantum key distribution system that is currently being developed by the European Space Agency, the European Commission, and it involves 20 companies in Europe, and IDQ is one of them contributing to this project. So there will be in this network a satellite that will beam down light to ground stations. So the link budget is such that there's a lot of loss. I think it's around 50 to 60 dB loss there. So you need to have extremely good single photon detectors in order to achieve this. And you need more than that. You also need a system you can deploy. The efficiency is important, and the time precision is also crucial for this to be a possibility. So now let's move on a bit more in the complexity or the kind of things that become more and more quantum. You can also distribute entanglement over optical fibers. This is an example of a feasibility test done using undersea fiber connections between Port Train and Southport, 224 kilometers. It's very interesting experiment. This essentially distributed entangled photon pairs from this end to that one right here. You need in that situation, again, high efficiency and very low noise. And this experiment was also using SNSPDs to make it a possibility. So really crossing borders here and physical borders is something that's possible. Again, in 2024 in quantum networks. Here's another example. It's set in a metropolitan environment where a source of entangled photons was placed here. So one entangled photon was sent over this link here, 35 kilometers, and the other was going over 15 kilometers to the Infinity Institute. This is done in a group of Sébastien Tanzili in NIST, sorry, not NIST, NIST. This is quite interesting. There's a lot of noise in these optical fibers, and they were nevertheless able to perform quantum key distribution over this link here. Challenge for the detection system, again, portability, efficiency, and low noise. Now, let's go even more quantum. Okay, we're going to add quantum memories, because if you want to make a fully quantum network and distribute entanglement to a greater scale, you do need the ability to synchronize the quantum information. The distribution of photons at a single photon level is always a probabilistic thing, because there's loss. So the quantum memories allow, in the simplified manner, to synchronize the quantum information. And here, the group of Hugues de Rietbatten in ICFO Barcelona has demonstrated such an elementary link. They have, in a nutshell, a source of entangled photon pairs. One is going into a quantum memory, the other one is going into an optical fiber, And we have the same thing on the other side. And these two photons here are going under a Bell state measurement. And that has the effect of swapping the entanglement to these two quantum memories that become entangled. And this is done in a heralded fashion. You know when you have stored the entanglement into a quantum memory. And recently, they have taken this into a metropolitan network by distributing light matter entanglement. Very fascinating experiment here. And again, lots of demand on the detection side. As you can imagine, and specifically here, ultra-low noise detection was a crucial thing in order to make this possible. Okay, all of this goes into the direction of a generalized quantum internet to distribute and use entanglement. I was telling you about this heralded entanglement possibility. Well, in order to realize this, you need the quantum light source. You might need quantum transduction, which means frequency conversion. So you might go from one wavelength to another because the light source might be at a given wavelength. Maybe the quantum dot light source is not a telecom wavelength. You want to transfer that to a telecom wavelength for optical fibers. You need the quantum memories, you need the detection, and the timing. If you have two such links, you can do a Bell state measurement that will swap the entanglement between this one and this one there. And you can imagine that this requires a lot of orchestration, synchronization, by software control and hardware control. So there's also this layer that needs to appear in the quantum network. You can make it with an arbitrary topology, and using that, maybe you can connect two things such as quantum computers in order to entangle them or to exchange quantum information for greater scale kind of processing. So this would be what the quantum internet is, given the building block that I explained to you. Speaking of quantum computer, now let me move on to photonic quantum computing and simulation in 2024. This is a very broad field. I can't cover everything. I just want to give you some idea about it. Okay, the first thing I want to talk about is boson sampling machines. These are machines that are designed to demonstrate a quantum advantage. Okay, they're not really necessarily useful, but they can demonstrate that we can do certain tasks in a computational fashion that cannot be performed using a classical computer. This has been performed several times already by academic and private commercial entities, and it really demonstrated the potential of the photonic approach of a quantum computer. So this was one of the first experiments, all free space optics, gigantic effort. Of course, you want to go towards an integrated approach here. This is an example here that is called the Gaussian boson sampler, where you use squeeze states of light going into a linear optical circuit, and you have light at the output, and you need single photon detectors that are efficient, but more than that, you need them to be PNR efficient in order to realize this task step. So this is a very important challenge for single photon detection to realize that kind of boson sampling machine. Moving further in the complexity, you can look at cluster state generation. How does this work? So you have single photon sources that you send into a linear optical circuit with detection, and there's a probabilistic process behind them. But if you succeed, you will have created entanglement there. You scale it up by bringing in more photons, more detectors, then you get more entanglement, et cetera, et cetera, et cetera, and you can entangle a lot of photons. In this, you can create this large resource called the cluster state, and you also have to go into 3D to create clusters that kind of look like this. So what do you need to realize is very, very challenging. I'm sure you will agree with that. From the detection side, you need scalability and also PNR detection. So there's different ways to realize that, but I think everyone is going to agree that you need photonic integration for this. So design fabrication, here I'm showing an example of Ligentech in Switzerland working on this. You need the packaging, the interfaceability, and the programmability. This is something that the company Quix is actually offering today. Then you need to scale into a system that integrates all the different components. I'm giving two examples here, the company in Paris, Quandela, and in London, Orca Computing, that are doing this. And you need to integrate the detection in there. So the challenge is this integration into these integrated quantum systems. Now, ultimately, if you want to have everything in scale to 1,000,000 qubits, you do have to go super big and bold and have everything integrated. That's what the company PsiQuantum is doing. They are integrating everything, including detectors, but not just that. There's also the control electronics nearby. There's the cryogenics and all of this. I'm not going to cover all of this here, but it gives you the scale of things that you need to address for this and that. Okay, now before I switch to Giovanni and Tile, what we do at IDQ is we have products and we want to enable quantum connectivity with photons. Our products are used for quantum networks, quantum computing, but also to quantum photonics in general. There's a very large range of end users doing research in the academics, in academia, but also in companies. We have these single photon detectors, SNSPDs, the cube, we have timing electronics, we have QPD boxes. Tyler is going to talk about that later on in the presentation. But first, we're going to start with Giovanni, who's going to tell us about some innovation that we have done recently on the SNSPD front. Okay, so I'll leave that to him. Tyler is going to come after that to tell us more about our product range, and in particular, a new product that we have just launched, which is a rack-mountable cryogenic system to have SNSPDs in them. Just before doing that, okay, we're IDQ. We started in 2001. We are a bit more than 100 people today in 4 locations, but mainly in Geneva, Switzerland. We develop products for quantum safe security, quantum technologies, quantum photonics. We sell to academics, companies, startups in industry. We are an experienced team of, we have an experienced team developing state-of-the-art detection systems since 2001. We've been delivering SPADs, detectors, since 2001 and SNSPDs since 2017. And the SNSPD activity really has become a big part of what we do. We're really proud of what we've been able to achieve and the impact that we've been able to have outside of the company in the world today. So we're happy to talk about it today. And we want to deliver excellence through innovation, performance, and reliability. Stop there. I'll hand over to Giovanni for the next part of the presentation.
Yeah. Thank you, Felix. And I hope everybody can see my screen properly. So thank you also Optica for organizing this webinar. As Felix said, it's a great pleasure to be here. And we are glad to have the opportunity to share our research with all of you. So I will start with a high-level introduction on the operation of an SNSPD. And here I focus on the conventional form of an SNSPD, which is what we refer to as a single pixel SNSPD. So this is a really long meander of superconducting nanowire to which light can be coupled via an optical fiber. In order to detect single photons, then we bias this detector at a specific current close to the critical current of the detector. And here you can see an example of a circuit that can achieve this. This current is needed in order for the absorption of a single photon in the nanowire to trigger this process where the entire cross-section of the nanowire becomes resistive. And it enables the current that was flowing in the nanowire to be diverted to the readout system, thus generating an output pulse that can be detected by a threshold discriminator. At this stage, when the current is shunted to the readout system, the nanowire has time to cool down, going back to this superconducting state and being able to again detect a new photon. As Felix already mentioned, single pixel designs have achieved remarkable system detection efficiency with very low noise and really good timing precision, which is highlighted by this the jitter parameter, which can be lower than 20 picosecond. However, in this design, there are still some limitation. And namely, the recovery time is still a bit too slow, which limits the detection rate of these devices to a few tens of megahertz at best. The really low jitter that I've showed also rapidly increases as you are increasing the detection rate of these devices. And moreover, achieving a proper photon number resolution with a single pixel device can have very serious practical limitation, which we would like to overcome. And especially addressing all these three aspects together would give us a real chance to unlock some new frontiers for optical quantum technologies. And indeed, as Felix already mentioned, there are applications that require these extra performances from these detectors. Photon number resolution it can become a key component for photonic quantum computing, and ultra-fast detectors are definitely needed for supporting ultra-fast quantum key distribution protocols. So in order to achieve both these features at the same time, we transition to an architecture that goes from one single pixel to several pixels. So we divide the same area into a plurality of pixels, and thus we can have both the capability to resolve different photon numbers, and also we can improve our detection rates. At IDQ, we are working on two different approaches in order to enable these new features. We have our line of parallel SNSPDs, where n pixels can be connected with only one readout line. And this particular architecture enables the output pulse of the detector to encode the information regarding the photon number impinging on the detector. So you can have a signal that's proportional to the number of photons that have been detected. And moreover, because you're splitting the area in between several pixels, you can achieve faster detection rates up to around 200 megacounts per second. The other approach is what we refer to as multi-pixel SNSPDs, where now we have n independent pixels, which have to be read out with n separate channels of our cryostat. And in this way, the PNR performance is achieved by just looking at how many pixels click in a given amount of time. And this enables the discrimination of photon number without any limitation on the light that is arriving on the detector. And also it boosts even more the detection rate that can be achieved with such device. So here I just have this overview to show you the differences between the two approaches. I will start focusing on the PSNSPD, but for both architectures, I will show you the advantages that they offer, and I will highlight some real-world experiments that have been enabled by using these detectors. So the parallel SNSPD have quite a unique architecture, which is in fact patented, where there are some nanowires, which we call active nanowires, which is the only part of this huge structure that is actually exposed to the light that we want to measure. And all these other structures, they form some additional nanowires and resistors, which have the function to minimize the current redistribution effects between these active pixels. So you can have some pixels here that are clicking, and the current in the remaining pixel, it's still not changing so much. By bringing all these pixels together in one line, then we can create directly inside the cryostat this overlap of the signals, creating this output at the output of our cryostat that has the clear advantage of having these different levels, which are representative of the amount of photons that were reaching the detector. Given this architecture, the first thing we focused on was to develop a mathematical description of the detector. Because at the end, everybody using such a detector will focus on the question, what is the probability of detecting n photons when n photons are sent? And so we find a way, with a very simple model, we find a way to link the photon counting statistics of the detectors, namely the probability to observe an n-click event, to the input light statistics. So the probability that there were m photons at the input. And this link is created by this matrix composed by all these P and M elements, which are fully describing all the possible probabilities of detecting n photons when m photons were sent. The model is really simple. It can be found in the reference that I have here. And the only assumption is that we have uniform light distribution amongst our pixels. So the pixels have the same efficiency. And this is ensured by this interleaved architecture that we use for all our PNR detectors. This model, as I mentioned, allows us to link these two quantities. And then once these numbers are known, we can link the collected photon statistics to the input statistics, and we can perform coherent state reconstruction. For example, in this case, what I'm showing you is that we can perfectly reconstruct coherent Poissonian light that we calibrated in order to send the detector. So we can fully rely now on this mathematical description of our detector also to reconstruct light that we might not know. So you can reconstruct unknown states of light if you use this detector in this way. But what is an even more demanding application of these detectors is to know single shot how many photons were incident on a detector at any given trial. And for this, what is really key is what we refer to as n-photon efficiencies. So these are the diagonal elements of the matrix, which give us the probability of correctly identifying the number of photons. And we can see that the model, if we measure a single photon efficiency of 90%, the model will describe our detector and these efficiencies, and we can have above 70% efficiency for 2 photons and around 50% with 3 photons. And this is already making this detector very appealing for photonic quantum computing, but also for other applications that might have a need to discriminate these photon numbers. And for example, we used this detector to improve the performances of an heralded single photon source. So here we have an SPDC source, which is pumped with a laser and produces entangled photons that can then be separated with a polarized beam splitter. And by using SNSPD in the heralding arm, I can take advantage of the possibility to discriminate single pair versus double pairs, which are much more frequent as you are increasing the pump power of your pulse. So we can then decide to herald only these photons that are actually single photons and ignore all the double pairs contribution. And by doing this, we can improve the source itself. We can reduce its autocorrelation function by around 26%. And we can also increase the heralding rate because we are able to then pump our source at a higher mu. And moreover, we also showed that by using only one SNSPD, we can reconstruct the thermal statistic of the source. So we verified this opportunity to use our detectors also in this aspect. However, we were looking at how we could make these devices even better, what more we could improve. And I'm really glad to be able to present you this new generation of parallel SNSPDs, which are based on a 28 pixel interleaved architecture. Here you can see an SEM image, and because now you have 28 pixels, you can see in the oscilloscope trace of the output of the signal 28 separate levels, which correspond to the correct operation of all 28 pixels. And now the point is that the goal of this detector is not to correctly discriminate between 20 and 21 photons, but it is really to improve every single performance that I've shown you before on an 8-pixel device. And because more pixels are always better for this architecture, we can now get a faster detector with performances that are stable at higher count rates, improved and photon efficiencies, and we still require only one coaxial line. For example, I can show you how the efficiency varies as a function of the detection rate for one of these devices. This is a typical curve that we can take in CW light. And from this curve, you can see the maximum efficiency of the detector measured, which is around 90%. And you can see how the detection efficiency remains above 80% until 55 megacounts per second, and it reaches 50% absolute efficiency at 230 megacounts per second. And this really makes this detector the state of the art with respect to speed, considering that we are using only a single coaxial cable to read it out, and you can have up to 16 of this detector in one of our cryostats. Moreover, we were able to demonstrate that the jitter of this detector, it's not impacted as much by the counting rate, the detection rate of the device. So we used our time tagger, the ID1000, to record this jitter, the jitter of the detector for different count rates. And we found that we demonstrated that it is possible to achieve a jitter below 60 picosecond for detection rates of 100 megacounts per second. And this for sure can make such that these detectors appealing for quantum key distribution or any protocol that requires high timing precision at very high detection rates. Lastly, we can see that there is a drastic improvement in our PNR performances thanks to the improved number of pixels. And here to show you this, I will compare the end photon efficiency of the device of the 8-pixel SNSPD that I presented previously with the ones that we can achieve with the new 28-pixel. And you can see drastic improvements all across the board for all these these end photon efficiencies. And once again, this can be really a game changer for applications such as Gaussian boson sampling or photonic quantum computing. And we really hope that these devices could have a real impact in these fields. These devices, they are great. I think I hope I have convinced you about this, but they have unfortunately one limitation, which is that for the mechanism of these, the creation of this output signal, in order for it to work properly, the light at the input needs to be confined. The pulse of the light needs to be confined within around 300 picoseconds. And there are applications where this might not be possible, and there are photons that might have a coherence time longer than this, for which you would still want to discriminate the photon numbers. And to overcome this, I will now switch to the other design that I mentioned at the beginning of my talk, which is the multi-pixel SNSPD. And here we managed to overcome this issue on the input light duration, while also enabling an even faster detection rate at the cost of a slightly more complex readout, because these pixels are operated independently. And for this, I've chosen to show you a multi-pixel SNSPD, which was made with 14 independent pixels. And it was specifically designed for operation for ultra-fast quantum key distribution. So the detector was supposed to achieve the highest possible count rate with the lowest jitter. It enables to have still the simple optical setup where there is only one fiber arriving to the detector. And the change in architecture means that now we can even perform PNR state reconstruction with long photons. And this is exactly what we demonstrated in our publication, where we were able to correctly reconstruct Poissonian light of 3 and even 10 nanosecond duration. So this was mimicking really the operation with photons that might have a long coherence time, that might come from cavity enhanced SPDC, spontaneous four-wave mixing, squeeze light. And these photons might really be needed in order to interface maybe with quantum memories, because these devices usually require photons that are very narrow band, which in turn translates to a longer coherence times. So possibly this detector could enable better operations of quantum repeaters and interface with quantum memories. Going back now to the performances that I mentioned that are relevant for our QKD experiment, this detector showed a remarkably low jitter of around 21 picosecond when operated at low count rate, and the jitter remains below 50 picosecond at a total count rate for the entire array of 320 megacounts per second. As I mentioned, there is a huge improvement in terms of detection rate, thanks to the independent operation of the nanowires. And we demonstrated an 80% single photon efficiency at 400 megacounts per second, and a 50% efficiency at 1.5 gigacounts per second, which is the performance that was really needed in order to perform the fast quantum key distribution that we were looking to enable. And our experiment that was performed in collaboration with University of Geneva and published in Nature Photonics showed that by using both our MP and SNSPD as the detectors in this protocol, we demonstrated a secret key rate of 64 megabit per second over a fiber link of 10 kilometers, and even 3 megabits per second on a fiber length of 102 kilometers. So this brings me now to the end of my section. I hope I've been able to spark your interest in what we do at IDQ, and I hope I've shown you a bit some of the ways that we can enable photonic quantum technologies. I let my colleagues now finish this talk, and it was really a pleasure to be here.
Great. Yeah, thank you, Giovanni. Thank you to Optica as well for hosting. Giovanni did a great job discussing some of the R&D work and innovation that we've done recently on our SNSPDs. I'm going to be talking a bit downstream of that about some of our products at IDQ. We offer a variety of products that are relevant to quantum networking and computing. First, we, let's see, turn on my laser pointer here. So first we have single photon detectors. So we've been talking about the SNSPD systems that we offer. These include the ID281 Pro rack-mountable system that I'm showing here on this slide, and that I'll describe in a bit more detail in a couple of minutes. As we've been talking about, SNSPDs really offer the very best in single photon detection in terms of detection efficiency, low noise, timing jitter, recovery time. We do also offer SPADs, single photon avalanche diodes in the near IR. We've been producing these, as Felix mentioned, for a bit over 20 years now. We have units optimized for telecom wavelengths, compactness, and cost effectiveness, or also extremely low dark counts. The unit that I'm showing here on this slide is called the ID cube. The form factor is a cube, and the dimension of each side is around 10 centimeters to give you a sense of the scale. We also, so that's single photon detection. We also produce QKD platforms. We're currently on the 4th generation of our QKD product line with modules tailored to different needs. We have the XG series, which is designed for production environments, ready to be integrated into a data center. We also have the XGR series. The R is for research, an extension of the XG series with additional flexibility designed with researchers in mind. We also have the Clavis and Cerberus modules implementing different protocols depending on your requirements for range and key rate. I'll also mention that we at IDQ produce timing and control electronics, especially including the ID1000 time controller, which offers an all-in-one time tagging, coincidence correlation, and delay pulse generation module. So in the remaining time for this talk, I will highlight 3 of our newer offerings that I'm especially excited about and that I think bring some real value to this space. First, an integration of our Clavis XGR QKD platform with external SNSPDs. Then I will talk about the rack-mounted ID281 Pro that we've foreshadowed a couple of times. And finally, I'll talk a bit about the productization of the parallel and multi-pixel SNSPD designs that Giovanni was presenting. So first, using our QKD platforms with external SNSPDs, the idea here is very simple. We make state-of-the-art QKD platforms, like the Clavis XGR shown here. We make SNSPD systems, like we've been talking about. Let's bring that expertise together and integrate the two. The ID281 Pro is our rack-mounted SNSPD system with a focus on easy integration, reliability, ease of use. The XGR, as I mentioned, is tailored to meet the needs of researchers with features like access to internal data and raw keys, modifiable parameters, interoperability through standardized interfaces for experimental networks, and it's an automated turnkey solution with user-friendly full-stack software. So what sorts of performances can we get when integrating these two systems? Really the key question, I suppose. So here is just a bit about that. We're showing here a graph of the secret key rate versus attenuation. And we can see that we're getting around 400, so these are typical performances, I should say. We're getting around 400 kilobits per second SKR at 12 decibels and over 40 decibels of dynamic range. Note that this data is using polarization insensitive SNSPDs that we have designed, which are optimized for QKD performance and specifically with the Clavis XGR. Note as well that our cryostat for the ID281 or ID281 Pro system does have 16 channels, and so therefore we can serve up to 5 Clavis XGR receiver modules in parallel with a single unit. So for example, if you wanted, a star topology with the SNSPD in the middle with 5 receiver stations, things like this are possible. For more information on this, I'll recommend a webinar upcoming with our colleague Florian, who will be discussing several use cases for IDQ's open QKD platforms with external detectors. And I've listed them here. If any of this sounds interesting to you, check it out. There's a QR code to sign up for the webinar, which is coming up on May 21st at 3 p.m. Zurich time. And note that this is external integration with SNSPDs I was talking about just now. You can also integrate these detectors with other, integrate these QKD platforms, that is, with other detectors, not just SNSPDs. So this could include the ID Cube series that I had mentioned previously, for example. These are, compact, affordable detectors that give the researcher access to a broader parameter set to play with, allow for extended gray box testing of the Clavis's BB84 implementation, for example. So yeah, if any of that sounds interesting to you, check out that webinar. But now I am going to transition to talking about the ID281 Pro. We're quite excited about this new product. The reason that we decided to develop this product was in response to some market trends that we're seeing. So as the field matures and moves towards more highly integrated quantum systems, we are seeing intensifying requirements around portability and integration. And it's really necessary to be able to have the same great functionality of the SNSPD platforms that we've developed so far, but with simpler operation and easier integration to these larger systems. This is especially important in fields such as those we're talking about today, quantum computing and quantum networking and communications. So here is the product, the ID281 Pro. It's an intuitive rack-mountable system designed for reliability, simple integration, and ease of use. Fully autonomous 24/7 continuous operation. We've really done a lot of work to simplify the system. And keep the installation and integration as simple for the end user as possible. We've got a whole new intuitive web UI for remote operability. The cryo unit shown on the right part of this slide is 8U tall and hosts up to 16 detectors. We also have rack-mounted options for a vacuum pump. That vacuum pump is unique to IDQ, and also a rack-mounted compressor, which is the Igloo compressor from AttoCube, which I think many of you will be familiar with. So we're quite excited about this. But of course, the best cryostat in the world, the best integrated system, doesn't matter unless the detectors, the beating heart, really have the best performance as possible. So to be clear, what I'm talking about here are detectors that we are offering as products that we are shipping out the door at a very high rate. So this is not just experiments we've done in the lab. These are products that you can buy right now. So we and I'll also mention that we can tailor these these specifications to the requirements of your application. And so we've got engineers who can work with you on choosing the right set of specifications for your application. So efficiencies over 95%. In some cases, even over 95%. So we're able to get very high efficiencies with these detectors. This is true for both our single pixel detectors and the PNR detectors that I'll talk about in more detail in a moment. Recovery times for our single pixel detectors of under 30 nanoseconds with under 30 picoseconds of jitter. And again, as Giovanni was mentioning, we've shipped systems that are under 20. Low dark count rates at 1550 nanometers. As an example, over 80% system detection efficiency with simultaneously under 1 count per second of dark count rates. And extended range. So we have detectors with that are optimized, based on the cavity for high efficiency in the range of 600 nanometers, or we can tune that for detectors with high efficiency above 2 microns. In each case, with hundreds of nanometers of high efficiency. Efficiency that's high over a range of several hundred nanometers. So that's the detectors. And we also have some options for the cryogenic platform. I talked a couple of slides ago about the ID281 Pro, our compact 8U cryostat. We also have our ID281 still available, which comes with two options: a sorption system with up to 40 hours of operation before needing to do a reset, which takes around an hour. That operates at around 1 Kelvin. And we also do have a continuous operation, or CO system, that goes round the clock at a bit under 3 Kelvin and hosts most of our detector catalog. Of course, we're happy to go into much, anybody who wants more information on these things, we'd love to chat more. Feel free to reach out. And now in a bit more detail, just to summarize what Giovanni has said about our parallel and multi-pixel SNSPDs, and specifically what is available as a product, and the use cases for each. So for our parallel SNSPDs, we consider these to be the most practical PNR and ultra high-speed solution for most applications, as long as the limitations on input light aren't a constraint for your application. So if coherence times and having the light arrive within 300 picoseconds for these pulses works for your application, then we believe that parallel SNSPDs have some very important advantages that make them the way to go. As we had mentioned, we can have up to 28 pixels per parallel SNSPD, and up to 16 of those units per cryostat, allowing for detection rates of over 200 megacounts per second per channel, which can be combined for extremely high detection rates across your experiment. For the most demanding applications, if you really do require this dynamic PNR that we were talking about, or the very highest detection rates, for an optical channel, then we do offer multi-pixel SNSPDs with 4 to 16 independent pixels with one readout line. If you're getting 16, that fills a cryostat. So this does offer very high fidelity PNR, as Giovanni had talked all about, very high detection rates, and it's the most versatile with no limitations on the pulse duration or spacing. So finally, if you wanted to learn more about any of this, there's our website, idquantique.com. You can check out our series of ongoing webinars that we host. These are, typically with, users of our systems presenting some of the cool science they're doing, enabled in part by our devices, which, we find really exciting and inspiring, and some of you hopefully may find interesting as well. If you'd like to reach out with any questions for us, if you're interested in a product or just want to know more, info@idquantique.com. And finally, we do put out a roughly monthly newsletter, and there's a QR code to register for that. That'll be things like links to upcoming webinars, any news, papers people have published using our equipment, things like this. So yeah, with that, thank you for your attention. I will hand it over to Felix for some concluding thoughts.
Super, thank you so much, Tyle. I'll finish, I'll be brief. So we're just putting this slide again. We spoke about quantum networks, quantum computing, quantum photonics in general. Giovanni told us about single photon detectors that have features that are useful for these two fields there and beyond. Tell us about the product. We are very excited about what we presented to you today. We hope you are as well. And I think it's also important to see that These technologies are challenging, they're very exciting. Developing quantum networks and photonic quantum computing is a global effort. Our part in this is to bring state-of-the-art and enabling single photon detection technologies to you. We'll be very happy to engage in discussion with you. If you have any questions, please reach out. And I'll continue with, I will finish with this on behalf of everyone at IDQ. Thank you very much for being here today.
All right. Thank you so much, Felix, and the whole IDQ team, Giovanni and Tyle. Let's jump into the questions. There are many of them coming through. Some of them I know you already answered, but let me just go directly to the question. The first question is, what is the efficiency, or what is the device efficiency of IDQ 281?
So all of our detectors will have an efficiency in the range of 80 to 90, and some detectors actually go towards 95 and sometimes even higher than that. So we are capable of offering certainly good performance with these detectors. There's no difference really between the normal detectors and the SNSPD or the SNSPD. They're all absorbing and working in the same way.
Okay, next question. How the efficiency varies with wavelength with SNSPD?
Yeah, very good question. So SNSPDs can be quite broadband. They can absorb over a very broad range of regions. But in order to optimize the efficiency, you need to make a cavity, a planar cavity. But it's still a very broadband cavity. So the efficiency will typically stay pretty much flat over a 100 nanometer range. Then it will taper down. Towards longer wavelength, it will go down not as fast as the shorter wavelengths. You have this kind of some asymmetry, but if you go on a website, on a brochure, you'll see trends about how this behaves. This being said, we can cover high efficiency over many wavelengths, around 635, 1550, and we also offer detectors that work at 2 microns as well with good efficiency.
Okay, next question. Is the 1 gigahertz SPD a reality and commercial product? What will be the #1 benefit to the industry?
So the answer is yes. It's a commercial product. It's something we can ship today. The #1 benefit to the industry, I hope we were able to give you some examples of that. I saw the question happen early on in the presentation. So we spoke about QKD, high-speed QKD. We spoke about also the need for something we didn't talk about that can benefit from that is optical communication at a very low light level, something that is relevant for DSOC, for instance. That's the kind of detector that may have an impact there as well. And just speeding up quantum computers in general, you can have these SNSPDs that play a role there.
Another question, how do you ensure minimal crosstalk when you talk about the NRA, or does it actually matter? Is there any limitation toward nanofab for multi-pixel devices?
So I'll ask Giovanni to answer that question. He's the best person to ask this one, to answer this one.
Yeah, thank you. It's actually a very good question. It's something that we really explored in our publication on the detector, the multi-pixel SNSPD. There are a few ways. So you can control these at a nanofabrication point of view by choosing a proper width of the nanowire, by making sure that they are spaced enough, that the thermal crosstalk is limited. Of course, you can measure it in order, you understand how much it is. And then you can also play with the bias current that you have in your pixels. So if your detector has a plateau, you are able to not have any compromise in the efficiency, so you can operate at slightly lower bias currents, not lose anything in efficiency, and drastically reduce the thermal crosstalk. So it's something you can control in a variety of ways. It helps to have more pixels also, and yeah, we wrote a bit about this in the publication. I encourage you to check it out for more details.
And it is part of our characterization in our operations. When we sell a detector like this, we do look at this, and we've worked hard to minimize it. So it is there, but the impact is really small.
Okay. Another quick question they have is, could you show the previous slide with the QR code? I would answer that one. The recording of the slides will be available in a day or two, so you can see the QR code over there. I think we have time for one more question, and I think that would be the last one. Are those detectors compatible with mass manufacture to accompany the booming in QKD needs if there is a boom?
Okay, so it will depend on the size of the boom. If we have to ship 1 million QKD systems next year, so we're gonna have a very big challenge in front of us. But typically speaking, the answer is there's a lot of scalability that we have worked on in the last few years, because in order to deliver them to the level that we have been to because of the demand, because of the fact that the product actually does have a lot of interest and impact, we had to solidify our operations there today. So for the SNSPD part, the answer is it can be scaled up. The SPAD part as well, there's also some challenges there to go to a very large number of devices, and here I'm talking about, even 100,000 QKD system will require some scaling up, but it is possible to do. One thing to mention is that the SPADs, the in-gas SPADs for QKD systems that don't use the SNSPD, which is most of the QKD systems, are based on the same technology that is used for APDs in telecommunication, right? So telecommunication industry for APDs is already there. So same kind of process and machine, special process, but same kind of process. So yes, you can have the same kind of scaling that you have for APDs.
Okay, thank you so much. I think there are a few outstanding questions, but I'm sure you will reach out to them with the answers offline. Thank you so much. This was a very informative and great talk, and we are very happy that you had this webinar for us. So with that, I would like to close the session today, and have a great day, everyone.
Thank you.
Yeah, thanks everyone.
It was a pleasure.
Bye. Thank you, everyone. Bye-bye.
Bye.